Hello, everyone. Welcome to the fourth lecture of AAE 301. In today's lecture, we will talk about Fourier analysis and Fourier synthesis. First of all, what is Fourier analysis and what is Fourier synthesis? Fourier analysis is the study of decomposing the signal into its corresponding sinusoids and amplitudes. And Fourier synthesis is the process of reconstructing the signal from its sinusoids and amplitudes. To help you understand how these two concepts works, let's take a look at this example on the left. So here on the left, we have a complicated signal. And if we run Fourier analysis on this signal, we can decompose this signal into 6 different sinusoids. And as you can see, the amplitude and frequency of each of these sinusoids are all different. And say now we have these 6 signals, and we are asked to reconstruct the original complicated signal. What we can do is we can run Fourier synthesis on these signals, and what it will give us in the end will be this complicated signal on the left. Okay, that was an overview of what will be covered in today's lecture. And in the following of the lecture, I will teach you how you can perform Fourier analysis and Fourier synthesis. And to do that, let's review some of the concepts that we have talked about in the previous lectures. The Lebesgue space. So the Lebesgue space L squared 0 to tau is actually a linear space with infinite dimension, and it contains all functions ft defined on the interval from 0 to tau, which satisfies this inequality here. So this inequality says the total power of the function f of t has to be finite within this interval from 0 to tau. We can also define the standard inner product for the Lebesgue space. So given two functions in the Lebesgue space, f of t and g of t, the inner product of f and g will be 1 over tau times the integral of f of t times the complex conjugate of g of t with from 0 to tau with respect to t. And now that we have defined the inner product, we can also look at the norm of a function f. So first, by the definition, the norm of function f will be the square root of the inner product of f and itself. And now we can substitute the expression for the inner product into this expression. And what we'll get in the end is the square root of 1 over tau times the integral of the square of the absolute value of f of t from 0 to tau with respect to t. And there's also one thing that I'd like to mention. There is an orthonormal set of vectors in the Lebesgue space, and this set of vectors is the set of functions psi k's. And here each psi k is equal to e to the negative I k times 2 pi over tau times t. And you can see that this psi k is going to be a sinusoidal function. Now let's see why this set of functions is an orthonormal set of vectors in the Lebesgue space. And to show that, we will have to look at two inner products. The first inner product will be the inner product of the function psi k and itself. And the second inner product will be the inner product of the function psi k and the function psi m. So here m is an integer that is different from the integer k. So first, let's look at the inner product of psi k and itself. So according to the definition of the inner product of psi k and itself will equal to 1 over tau times the integral of e to the negative ik times 2 pi over tau times t times the complex conjugate of e to the negative ik times 2 pi over tau times t. And we integrate this from 0 to tau with respect to t. And if you work out the integral, you will see that in the end, this will equal to 1 over tau times tau, which is 1. So that means that each vector in the Lebesgue space will have, so that means that the norm of the function psi k is equal to 1. Now let's look at the other inner product, the inner product of psi k and psi m. Again, according to the definition, we can obtain the expression that is shown on the right here for this inner product. And again, if you work out the integral, you will see that in the end, this inner product will be 0. So that means the function the vector psi k is orthogonal to the vector psi m. And these two conditions are exactly what we needed to say that the set of functions psi k is an orthonormal set of vectors in the Lebesgue space. Now let's take a closer look at the functions in the set psi k. And in particular, let's look at this function psi1, which is equal to e to the negative I times 2 pi over tau times t. And by Euler's formula, this is equal to cosine of 2 pi over tau times t plus I times sine of 2 pi over tau times t. And you can see that this is a periodic function with the period equals to tau. And now that we have defined the period, we can also define the frequency of the function, which is given by 1 over tau. And similarly, we can define the angular frequency omega naught as 2 pi over tau. And now we can substitute this omega naught into the expression of psi k. And you can see that in the end, psi k will equal to e to the negative I k omega naught t. And from this expression, you can see that the angular frequency of psi k is an integer multiple of omega naught. And for this reason, we say omega naught is the fundamental angular frequency of these functions. Now, you may be wondering, why do we care so much about this set of functions or vectors? And it turns out that this set of vectors or functions, psi k's, is an orthonormal basis for the Lebesgue space. This means that any function f in the Lebesgue space can be expressed as a unique linear combination of psi k's. Basically, that means that we can now write f of t as a summation of ak times psi k, and k is from negative infinity to infinity. And here, because we know psi k is equal to e to the negative I k omega naught t, so we get this expression at the end. And this expression at the end is exactly the Fourier series representation for the function f. And inside this representation, the coefficient ak is the set of coordinates of the function f in the Lebesgue space under the orthonormal basis psi k's. And in Fourier analysis, this set of coordinates are called the Fourier coefficients for f. Here, each coefficient ak can be computed by the inner product of f and psi k. And that is equal to 1 over tau times the integral of f of t times the complex conjugate of e to the negative I k omega naught t from 0 to tau with respect to t. And essentially, the Fourier coefficient ak tells us how much of psi k does the f have. And for this reason, ak is also referred to as the amplitude of the angular frequency k omega naught. Another thing that I like to mention is the Parseval's formula. Now with the orthonormal basis psi k's, the Parseval's formula for the Lebesgue space is given by the summation of the square of the absolute value of ak from k equals to negative infinity all the way to infinity. And that is because the kappa set in the original Parseval's formula is the set of all integers in this case. And now let's take a look at theorem 1 on page 6. So here theorem 1 essentially provides a summary of what we have talked about so far. And they can be summarized in words, and it is any function f in the Lebesgue space can be decomposed into a linear combination of sinusoids whose frequency are integer multiples of the fundamental angular frequency omega naught. And this is exactly the core concept of Fourier analysis. Now that we can obtain the Fourier coefficients for the function f, we can draw a graph called the power spectrum for f. And the power spectrum for f is going to be the graph of the square of the absolute value of the Fourier coefficient with ak with respect to the set of integers k. And this power spectrum will reveal the power of the sinusoidal components of f at different frequencies. So now let's look at the example that we have seen previously. After running Fourier analysis on this complicated signal, we can decompose this signal into 6 different sinusoids. And the power of each of these sinusoids can be clearly observed by looking at the power spectrum of the function f. So here on the horizontal axis is the index of the integer, and here in the vertical axis is going to be the square of the absolute value of the Fourier coefficient ak. And you can observe from the power spectrum that the sinusoidal components of the function f has a higher power at angular frequencies equal to 0 and 6 omega naught and negative 6 omega naught. Now let's take a look at another example. In this example, we will be looking at a square wave function. So for this function, its value is equal to 1 when the value of t is in between 0 and pi, and the function value will be -1 when the value of t is in between pi and 2 pi. And if you plot this function, you will get something that looks like this. So you can see when the value of t is in between 0 and pi, the function value is 1, and when the value of t is in between pi and 2 pi, the function value is -1. And in this example, I'm going to show you how you can obtain the Fourier series representation for this function. And by that, I mean, I'm going to show you how you can determine the Fourier coefficients for this function. And after that, I will show you the power spectrum of this function, as well as how you can find a Fourier series approximation for this function. Okay, let's begin with the period of the function. So the period of this function is equal to 2 pi. So here we have tau equals to 2 pi. And this implies that the fundamental angular frequency of this function, omega naught, is equal to 2 pi over tau, which is 2 pi over 2 pi, and that's 1. And the Fourier series representation for this function is given by f of t equals to the summation of ak times e to the negative I k omega naught t, and k is from negative infinity all the way to infinity. So this is the general Fourier series representation that we have obtained from our previous discussion. And now we substitute the value of omega naught into this expression, and we will get this expression below, which is the summation of ak times e to the negative ikt, and k is from negative infinity all the way to infinity. And now we will determine the Fourier coefficients. So we will start with A naught. So A naught is equal to the inner product of f of t and e to the negative I0t. And if you and according to the definition of the inner product, this will equal to 1 over tau times the integral of f of t from 0 to tau with respect to t. And if you work out this integral, what you will get in the end is 1 over 2 pi times pi plus negative pi. And so this will end up being 0. So that means A naught is 0. And now let's look at AK. So AK is going to be the inner product of f of t and e to the negative IKT. And again, we can follow the definition of the inner product. And what we will get is going to be 1 over tau times the integral of f of t times e to the IKT from 0 to tau with respect to t. And again, if you work out the integral, you will see that in the end, AK is going to be negative 1 to the power of k minus 1 over I pi k. So here we can have a small summary for the Fourier coefficients. Essentially, when AK is going to be 0 when k is even, and AK is going to be negative 2 over I pi k when k is odd. Now that we have determined the values of the Fourier coefficients, let's substitute these values back into the Fourier series representation. Because we know AK is 0 when k is even, so for this dimension here, we only have to care about the odd number case. So here we write this, we write the summation of odd case only. And then this summation can be broken down into two parts. The first part is the negative odd case, and the other part is the positive odd case. And here we can change the variable to make this a summation to be a positive odd k as well. So here this we just basically add a negative sign in front of the k here, so that we can change the summation from negative odd case to positive odd case. And now that we have both summations to be positive odd case, we can combine these two terms and we will get something like this. And now we substitute the value of a negative k and a k into this expression. And what we will get is these two products here. And we are gonna call the first product alpha. Now, if you look carefully enough, you will see that the second product is actually the complex conjugate of alpha. And so here we are actually summing a complex number and its complex conjugate. And we know that if you sum a complex number with its complex conjugate, what you will get in the end is 2 times the real part of the complex number. So here we have 2 times the real part of alpha. And in this case, the real part of alpha will be 2 over pi k times sine of kt. And that's why here we will get 4 sine of kt over pi k in the end. And now we can apply another trick to eliminate the odd k in the summation. So we know that any odd number, any positive odd number can be expressed as 2k prime plus 1, and let k prime to be from 0 to infinity. So here we will basically just replace k by 2k plus 1, and with that trick, we can now write the summation to be from k equals to 0 to infinity. And this is the Fourier series representation for the square function f. And we can also compute the total power of f of t. So the total power of f of t will be the inner product of f and itself. And according to the definition of the inner product, it will be equal to 1 over tau times the integral of squared of the absolute value of f of t from 0 to tau with respect to t. And again, if you work out this integral, you will see that it will end up being 1 over 2 pi times 2 pi, and that's 1. So the total power of the square function is 1. And also we have this Parseval formula that tells us that the total power of the function f will equal to the summation of the square of the absolute value of the Fourier coefficient ak, and k is from -infinity to infinity. And again, recall that ak is 0 when k is even, so we only have to care about the odd case. And next, we substitute the value of ak into this expression. In the end, we will get -2 over ik pi, and we look at the square of the absolute value of this complex number, and we will get 4 over k squared times pi squared. And here the summation is about all the odd case. And again, we can break this down into two summations like we did before. So the first summation will be the negative odd case, and the other summation will be the positive odd case. And we can apply the same trick by flipping the sign of the negative odd case. And in the end, we will be able to combine the two summations into one. And so that's why in the end, we will get 2 times 4 over k squared times pi squared. And the summation will only be about the positive odd case. And in the end, we can apply the same trick to discard the positive odd case. We do that by replacing k by 2k plus 1, and we can then let k to be from 0 to infinity. And so that's why in the end, we have this equality that says 1 will equal to the summation of 8 over the square root of 2k plus 1 times the square root of pi, and k is from 0 to infinity. And if we move the pi squared in the denominator on the right-hand side to the left, we will get this beautiful equation that says pi squared will equal to the summation of 8 over the square root of 2k plus 1, and k is from 0 to infinity. Okay, now I'm going to show you the power spectrum of the square wave function. So here, this graph here is the power spectrum of the square wave function f. So again, on the horizontal axis, you have the integer index k, and on the vertical axis, we have the square root of the absolute value of the Fourier coefficient ak. So you can see that for this square function, the sinusoidal components have higher power at lower frequencies. And you can see that the power of the sinusoidal components will decrease as the frequency increases. Now let's take a look at the Fourier series approximation for the square function f. So the Fourier series approximation for the function f is given by this function Pn of t, and Pn of t is equal to the summation of 4 times sine of 2k plus 1 times t over 2k plus 1 times pi, and k is from 0 to infinity. And here I'm going to show you what the approximation looks like when n is equal to 0, 10, and 20. So here in this graph, there are 4 different lines. The blue line is the function f of t, which is the square wave function. And the red line is the approximation function p naught. And the yellow line is the approximation function p10. And the purple line is the approximation function p20. So you can see the approximation function p naught is a pretty bad approximation for the square wave function. And as we increase the value of n, you can see that we will get a better approximation for the square wave function. And as we increase the value of n from 10 to 20, you can see that this approximation gets even better. In order to quantify the goodness of the approximation, we will have to look at the approximation error. Now recall that if the function has a Fourier series representation as the summation of ak times psi k, and k is in the kappa set, and here kappa is an integer set, and the approximation function p is equal to the summation of ak times psi k, and k is in the kappa 1 set, and kappa 1 set is a subset of the kappa set. Here we are going to look at the square of the error between the original function and the approximation. So now we substitute the expression of f and the expression of p into this error equation, and you will see that what we will be left with is going to be the summation of alpha k times psi k, and k is in this kappa 2 set. And kappa 2 set will be the kappa set excluding the kappa 1 set. And then according to the Parseval's formula, we know that the square norm of this summation will equal to the summation of the square of the absolute value of ak times the square norm of psi k, and k is in this kappa 2 set. So this means that the difference between the original function f and the approximation p will equal to the square root of this summation here. And now let's see how we can apply this result to compute the approximation error of the square wave that we have just seen. So in this example, f of t is equal to summation of 4 over pi times sine of 2k plus 1 times t over 2k plus 1, and k is from 0 to infinity. And its approximation, on the other hand, will be summing from k equals to 0 all the way to k equals to n instead. Oops. In this case, the kappa set is going to be the set of all integers, and the kappa 1 set will be the set of integers from 0 to n. And the kappa 2 set will be the set of integers from n plus 1 all the way to infinity. And also in this case, the coefficient alpha k is 4 over pi times 1 over 2k plus 1. And the psi k function is equal to sine of 2k plus 1 times pi. And so in this case, the square root of the absolute value of ak will be 16 over pi squared times 1 over the square root of 2k plus 1. And the squared norm of psi k will be 1 over 2. And here I skip the computation, but you can verify this yourself. And I believe in the end, you will get 1 over 2. So that means that approximation error between f and pn will be the square root of the summation of 8 over pi squared times 1 over the square root of 2k plus 1, and k is from n plus 1 all the way to infinity. I hope with this example, you will be able to understand how Fourier analysis works. And you can also practice how to apply Fourier analysis in homework 2. And before I end this lecture today, I like to talk about something else. Here, I like to mention that when the function f is a real value function, and then its Fourier coefficients are going to satisfy some certain properties. And these properties are, first, the Fourier coefficient A0 is going to be real, and also the Fourier coefficient AK is going to be equal to the complex conjugate of the Fourier coefficient A negative K for all integer Ks. And if you are interested about how these properties are obtained, you can look at the proof on page 14. And also, in some other applications, f may be a function in the Lebesgue space L squared from negative mu to mu. So basically, that means that f of t is defined on the interval from negative mu to mu. And here mu will be a positive real number. And the Lebesgue space will contain all functions that satisfy this inequality shown here. And for functions in the Lebesgue space L squared negative mu to mu, the Fourier series representation for a function f will be the same, but how you compute the Fourier coefficients will be slightly different. And you can follow equation 7 to compute the Fourier coefficient AK in this case. And also there will be a change to the Parseval's formula. And if you are interested, you can look at equation 8. Okay, this is the end of today's lecture. And I hope to see you in the next one.